Good morning, everyone. Hopefully you guys are doing all right. Looks like we have a few people in, maybe waiting on a few more. If you wouldn't mind just give me a green check, make sure everything's going okay this morning, and then we will get started. Perfect. A few of you submitted learning guides yesterday. I want to apologize right off the bat. I didn't have my settings in Moodle correct. So normally when you submit it, it sends me an email and then I can go in and mark it right away. I forgot to turn that setting on, and then I got in this morning and saw that nobody had submitted it, and I'm like, oh no. So I went and checked, and I had a few. So I got a couple of them marked and set out a few passwords for you guys. And if you had submitted yours yesterday, your learning guide for Unit 6, I'll get to it before lunch today for sure. So I apologize for not getting to that any sooner than I did. So there you go. Yes, I got you Abby's this morning. You were the first one in, so the first one marked. Is Mrs. Woods done, right, guys? I'm not like stealing her thunder here. There's just not very many of you, and I was just, I don't want to get going if she's still plugging away. Perfect, thanks, Taylor. All right, so what I'm gonna do is I'm gonna start Unit 7, and then when I'm done this lesson, if you have any questions from, okay, thanks, Taylor. If you guys have any questions about the last unit, I'd be happy to go through them, but I just want to get through this stuff. I'm gonna kind of warn you, I'm sure if you've printed it off, you've noticed that everything looked like really long. There's a ton of pages for each lesson. Now, this is kind of a bit of a problem with the course built into Moodle here and then learning out of the textbook. The course that we're doing, basically it condensed a few of the textbook sections into one unit. So basically my lessons are designed from the textbook, so I had to kind of modify them. So they might seem a little bit long, and we might have to skip a question or two, but I wanted to just make sure there was more than not enough. So if I kind of just say, we're not doing this one, don't sweat it. There was another one like it, so we can just, maybe do one instead of two of each. Yeah, it is pretty long. But there's lots of really big graphs and things too, and it's just one of those things. So the graphs take up a bunch of space, and I guess it's kind of good news, bad news. If you have been enjoying the graphing we've been doing in the last 2 units, we have another unit of it. There's a lot of algebra involved in Unit 7 though, so it's kind of one of these things. If you're good at manipulating equations and solving for variables and things like that, then you're not going to have any issues with this, but it can get a bit tricky. But the good news is, again, it's just lines that we've been dealing with, so it's kind of more of the same. It's just a little bit of algebra. So what we're going to do is we're going to run through this, and then I'll go through anything you guys had from the last unit if there's any time, and I hope there will be some time. So let's just jump into it. The solution of a linear system. When we talk about solutions of systems, it all kind of sounds scary, but really it's quite straightforward. There's 3 scenarios you're going to encounter, and we're just going to look at all the different ways to find the 3 scenarios. That's it. If you boil this whole unit down to one idea, is just 3 scenarios. If you can identify which scenario you're working with, you should be fine. So the solution of a linear system can be graphed on the same grid. If 2 lines intersect, the coordinates of the intersection are the solution. So it's just that easy. If we have 2 equations and we plot them on a graph, where those lines cross is the solution of the system. The idea is it's basically one point that will satisfy both equations. So let's look at an example here. We've got 2 lines. They're not in any special form. 3x plus 2y equals negative 12, and negative 2x plus y equals 1. And one thing that you'll notice maybe right away here is that we've labeled both of these lines 1 and 2. And again, the labels are just arbitrary. You could call 2 1 and 1 2 if you wanted. But when we have the lines, we're always going to have at least 2, and it's important to kind of figure out which one's which. So just at the very beginning, give them a label, 1 and 2, and then go from there. So the set of points to satisfy equation 1 lies on its graph. The set of points that satisfies equation 2 lies on its graph. So the set of points that satisfy both equations is where the two graphs intersect. So we have a little graph here showing these two lines. We have the equation of the first line here, and we have the equation of the second line here. So one's red and one's blue. And you can see that they both cross right here. And that is the solution to this system. So we make it sound like this big deal. Solution to a system of equations. It's just where the lines cross. And if we look really carefully there, we can identify that point with an ordered pair. So just an x and y coordinate. So let's look and see if we can kind of figure out where these things are crossing. So if I look up here to the x-axis, I'm at -2, and I look over here to the y-axis, I'm at -3. So that point is -2, -3. So that is the point of intersection of our two lines. Taylor threw it in chat, perfect. Kind of like when we were factoring a few units ago, a really cool thing about this unit is that we can always put the point into each equation and see if it makes the equation true. So we can always check our answer. So you get to the end, it asks what was the solution to the system, you find a point, in this case it's -2, -3. We can plug that point back into each equation and see if it makes each equation true. And we're going to do that right now. So let's check both of these things. The first equation we had was 3x plus 2y is equal to -12. And the second equation that we had was -2x plus y is equal to 1. So what we want to do is put our point into the equation. So where I have an x, I'm going to put in my x value, which was -2. And then where I had my y, I'm going to put in my y value, which was -3. And I'll just do this first one and then we'll look at the second one after. So 3 times -2 gives me -6. 2 times -3 gives me -12. -6 again, sorry, getting a step ahead of myself. Equals -12, and then -6 plus -6 equals -12. So I get -12 equals -12. And that is just a really quick way to see if the point that we found is actually on that line. Sometimes it's going to be hard to figure out where that point is and it might not be on the line. So if we got something like, -12 is equal to -3, well, then we made a mistake and there's something wrong with that. So we can go back and look at our point again. But in this case, they were both equal, so that works out. So it satisfied one of our equations. It needs to satisfy the other. Why did I put the -6 in brackets? It was just to make sure I was careful with my signs. I could have written it as -6 like that. I just wanted to maintain this plus sign that I had up above. And then 2 times -3 is -6. So I was just trying to be careful there with how I wrote that down. Let's look at the next one. The next line, we have 2. We're going to substitute in an x. We're going to substitute in our y. In this case, x is -2, and then -3. Following my order of operations, I'm going to multiply these things. -2 times -2 is +4. It's -3 is 1, and I get 1 as 1. So it turns out that the point I picked, it satisfies both of my equations. Once I put it in, I solved, and both sides were equal. So that means that that was the right answer. If I had gotten something different, like -1 equals 2, well, that's not true. So the point wasn't actually on one of those lines. And that's just how we do it. So let's maybe just write down a note here. Since both equations pass the check, we know that -2, -3 is the solution of the system. So if we were to, go through this process, we were to identify a point that we thought was the solution, and then we substituted in and we checked, and we found that on one of the points, maybe like this 12, 12 here, we found it to be 12 equals 12 or -12 equals 12. If we had something like 1 is equal to 3 over here, and we knew that that was wrong, what that would mean is that the point we found was on this line, but not on this line. That's why we would end up with a number that didn't equal what it was supposed to. So hopefully that doesn't happen. Hopefully all of the solutions you have always work out. But if it doesn't, if it works out for one and not the other, it just means that point was on the one line, but it wasn't on the other line. So just something to keep in mind as you're working through these problems. So there's going to be sort of different methods that we look at for each of the ways to solve these equations. Today we're gonna look at graphing them to solve. Tomorrow we're gonna look at using an elimination method to solve them. And then on the following day we're gonna look at substitution. So all we're doing is just solving systems of equations. We're looking at different methods to do that. And like I said, there's only 3 scenarios that work out. Alex is asking a question, what doesn't work for either one of them? Well, then that means that the point wasn't on either line. So to kind of just draw a graph quickly, you would end up with maybe a system like that, and then you said, okay, maybe the point is right here where the intersection, and you tried it out, but maybe the point that you checked was right there, and your lines just weren't very good lines. So that means that neither one of them would come back as true, so your check wouldn't work because your point actually wasn't on either line. If one of the solutions worked out and the other didn't, that would be something like this, where your point was on one line, but it wasn't on the other line. If you get it right, then it turns out that both of your solutions will become true. So let's look at graphing these 2 lines. Now, we've spent some time graphing in the previous unit. You see how these kind of build on one another. I've been given 2 equations, and there's lots of different ways to graph lines. I could find the x and y intercepts. I could convert them into slope-intercept form. It doesn't matter which way you do it. Personally, I like slope-intercept form the best, so that's what I'm going to do. So before I get started, I'm going to label my lines. I'm going to call this one number 1 and this one number 2. And I'm going to convert line number 1 into slope-intercept form. So I get x plus y is equal to 8. I'm going to move the x to the other side, and I'm going to get y equals, I'm going to sneak it in front, negative x plus 8. So I know I have my slope, and I have my y-intercept, and I'm going to plug that onto my graph here. So the y-intercept's 8. I'll go 1, 2, 3, 4, 5, 6, 7, 8. There we go. Now, because we're going to look for the intersection of these 2 lines, it's really important that we're very careful with how we're graphing these lines. We want to make sure everything's lining up as it should. All right, I have a slope of, even though there's nothing in front of the x here, I see that I have this negative sign. So this is kind of like -1 over 1. So I'm going to rise down 1, and I'm going to run 1, and I'm going to have another point here. because it's -1, my rise isn't going up, and I go across. Always kind of like to do a couple points. Break out your rulers, sides of your calculators, whatever you have. The more accurate your line is, the easier your life will be in this unit. And you're going to want to draw it all the way across the graph because you don't know where that other line is going to end up or where the intersection is going to occur. So you want to make sure that you draw it all the way across the graph because somewhere on that graph your lines are going to intersect, and if you don't know where, you might as well just go all the way across. All right, let's look at equation number 2 here. 3x minus 2y is 14. Now, I'm kind of tempted to put it into, to find my x and y intercepts and go from there, but because I converted it, the previous one into slope-intercept form, I'm going to do that here as well. Now, I think it was Ava that asked a question like this the other day, why did I move everything to the side I did? In the previous question up here, I moved everything over to the right side because my y was positive on the left, but now my y is negative on the left. So what I'm going to do is do something a little bit sneaky. I'm going to add 2y to both sides to make y positive over here on the right side. So I'm just kind of thinking a bit ahead. You get 3x, my 2y's go away. I get plus 2y, and then positive 14. Trying to get that y by itself, I'm going to subtract 14 from both sides. So I get 3x minus 14 is 2y. And then finally, I'm trying to get just y, so I'm going to divide everything by 2. So I get 3 over 2x minus 7 is equal to y. 2's just divide out to give me 1. So even though my y is on the right side, it's in y as mx plus b form. I have my slope, I have my y-intercept, so I'm going to go ahead and plot those things. My y-intercept's -7, so I'm going to go down 7. 1, 2, 3, 4, 5, 6, 7. And my slope is 3 over 2. So I'm going to rise 1, 2, 3. I'm going to go over 2. And I'm going to draw another point. I'm going to do this one more time just to make sure I'm getting everything lined up properly. Rise 1, 2, 3, over 2. All right. Again, I'm going to break out my ruler. Try to get this as close as I can. To a grid point there. So it's a little bit faint, but you can see pretty well what's going on here, I think. So it's asking me to identify the point of intersection. So I'm interested, the solution to the equation is where these lines cross. Now, because I'm drawing on a tablet, it's not that great. I was supposed to go through that point, but I missed by a little bit. If I use my slope again, rise 3, run 2, I'd end up there. So although my line doesn't indicate it, I was hoping to go through this point here. Abby's putting in 6, 2. Taylor got 6, 2 as well. Let's take a count. 1, 2, 3, 4, 5, 6, 1, 2. So if you had drawn this very carefully, you would have ended up getting an intersection at 6, 2. So that is what we believe our solution to be is 6, 2. It's a point that satisfies both lines. It's on both of my lines. To solve a system of linear equations, we find the point of intersection. So where those two lines cross. Now again, the great thing about this unit is we can always check to make sure our answer is right. very rarely in math, well, not rarely, we did it in the factoring unit, but we have the ability to actually check to make sure we've done this correctly, so we'd be crazy not to check. So I'm going to just scroll down here and write my two equations. I had equation number 1, which was x plus y is 8. And I had equation number 2, which was 3x minus 2y was equal to 14. So I'm going to plug in my point. So I'm going to get 6 plus 2 is equal to 8, and 8 is equal to 8, so that's good. And then for this guy, going to be a couple more steps. So we get 3 times x, our x point was 6, and 2 times our y point, which was 2, is equal to 14. So we're going to have to see if that works out. 3 times 6 gives us 18. Negative 2 times positive 2 gives me negative 4 equals 14. And 14 equals 14. So it turns out that the solution that we found was indeed the correct one because it satisfies both equations. And that's why it's really important to draw our lines carefully. It's just going to make your life easier in the long run. There is 2 more examples here, and I'm just going to maybe pick one of them. Let's just do example number 2. We'll skip 3 because there's a few of the other ones I want to do as well. And maybe if we have time, we can come back to it. So let's look at the next example here. This is one of these examples that people make fun of, I guess, because it's like a plane left Regina at noon, traveling 1,400 miles to Ottawa. Gives you a speed, 400 miles per hour. Another plane's leaving Ottawa at the same time, travel to Regina at a slower speed, 350. We want to know where the 2 planes are going to pass one another. That's essentially it. And one really nice thing about this question is it gives us the equations for both of these lines. Now, later on in the unit, you're going to have to come up with these equations on your own. But for now, just because we're interested in just solving them, we're going to give them to you. So I guess that would probably be the most difficult part of the unit, was coming up with the lines, the distance sort of equations. But we're going to do this just the exact same way we did the other one. We're going to label our lines. We have 1, we have 2. We're given that d is the distance from Ottawa and t is the time in hours. We're going to graph the system. So a few things we should do. We should probably label our axes, figure out what's going to go where, and yeah, going back 2 units to just graphing in general. I have distance and time. Almost 100% of the time, we'll go with 99% of the time, we're always going to put time on our bottom axis, or our x-axis. So I'm going to do the same thing here. Time. And then I'm going to put my distance on this axis. And my distance is going to be measured in kilometers. Looks like everything for my time is going to be measured in hours. I'm not distance in kilometers, it's distance in miles. We're dealing with imperial here. Apologize for that. So distance in miles, and then time in hours. How did I know to pick miles and hours? Well, I have miles per hour, so we'll just go with that. All right, some other information I have. I have a distance of 1,400 miles is the kind of the maximum. That's how far the cities are apart from one another. So if I'm going to be trying to figure out where my plane is, it's always going to be between 0 and 1,400 because that's the only information I'm given. And then the time, we're just going to have to kind of wing it and hope we get it close because it doesn't really give us any indication of how long this trip is going to take. We could probably use the information and just kind of figure it out, but we know we're going to have 0 distance down at the bottom, and then we're going to end up with 1,400 somewhere up near the top. So what if I go up by ones? How many boxes do I have? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Let's like it was planned. We have 200, 300. I'm just going to write every other one just to make some room here. 600, 800, 1,000, 1,200, and 1,400. So that works out. Maybe breaking out some just quick mental math. If somebody's traveling at 400 miles in an hour and I'm traveling 1,400 miles, how much time is that going to be? So every hour I travel 400 miles. How many hours till I get to 14? So I'm thinking 400 miles per hour times 4 hours would be 1,600 miles. So I'm looking at between 0 and 4 hours essentially. So I'm going to break my graph up. Time in hours, I'm looking at 4. So do every 2 spaces in an hour. That's 1 hour, 2 hours, 3 hours, 4. That'll work. I'm not going to utilize the entire graph like I'd like to, but that's going to be kind of close enough. Okay, that was a lot of work just to set up our graph, but these are the things we need to do. If we look at the equations we have, these are both in slope-intercept form already. The exception here is that the second equation has no y-intercept. So what we can do is just take equation number 1, which is going to be distance is 1,400, which is going to be my b, minus 400t. So this is my m, this is my b. I'm going to plot my b, 1,400, my y-intercept. My slope is going to be negative 400 over 1. So what I'm going to do is go 14, 12, 10. I've gone down 400, and I'm going to go across 1 hour. I have another point here. I'll maybe do this another time. I'm going to go down 2, 4, across another hour. Down 2, 4, across an hour. There we go. So I have 4 points using my slope and my y-intercept, and I'm going to go ahead and connect those points with a line. That's good. The second equation I'm given is distance is 350 times time. So this one has a slope, but my y-intercept is just 0. It's not there, it's missing. So I'm going to start at the origin. My rise is going to be 350 over 1. 350 miles every 1 hour. So I'm going to go up 200. There's 3, there's 50. Right there, I'm going to go across to 1 hour. I'm going to go up 1, 2, 350, and over 1. There we go. We have our point of intersection. Oh, that didn't go over enough. 1, 2, 3, 50 over 1. It's a bit better. So there we have it. Our point of intersection isn't on a grid point, which we didn't really expect it to be because we made the graph ourselves. So what we're going to have to do is just estimate it the best we can. And that's all we can do. It's kind of difficult reading off graphs sometimes. They're not super accurate. So the questions. Use the graph to solve the problem. When do the planes pass each other? How far away are they from Ottawa? So when the planes pass each other, the first question here, each one of these lines indicates where the plane is given any particular time. Well, my second point didn't go over a full hour. That's why this isn't lining up very well. I only went over half an hour. Try that again. 1, 2, 350. That's looking better. All right. So when the planes pass each other, when is asking me for a time. I'm going to go down to my time axis and look at where it is crossing this axis. So it's just before 2. So if I were to estimate what that is, I would say, well, that looks like about maybe 1.9 hours. And that's the best I can do here. There's no sort of, super accurate graph that we've drawn. It's just an estimate. You're looking at a graph, you're trying to figure out exactly where it is. And then how far away from Ottawa are they? We're given the distance from Ottawa is this axis here, so I'm going to go across. It's just above 600. It's below 700. Maybe in the middle of 6 and 7, we can call it 650. In this case, we're dealing with miles. And that's all we're asked to do. We could convert this 1.9 hours into hours and minutes if we wanted, or we could just leave it as 1.9 hours. I'm just going to leave it there. The idea here isn't that the solution is highly accurate. Could you draw those two lines? Could you figure out where they intersected? Can you estimate that point? And that's all we're expected to do here. So, given the information we have, that's what we got. So there we go. I'm going to take a pass on example 3 for now because I want to do a few of the additional examples on the next page. We might come back to example 3 later on when we start to develop systems of equations, but for now we're just going to leave it. The next page actually has some questions on it that I would like to do, because they're really similar to the ones you're going to see in the learning guide today. So, solve the following system by rearranging to slope-intercept form and graphing. So generally speaking, slope-intercept form is going to be the easiest one to do. So what I would like you guys to do, because graphing these lines is exactly what we just did, I would like you to attempt this example, and then we'll get you to come back and let me know what you guys ended up with for a solution. So if you're feeling brave, you can just go ahead and plot those two lines, figure out the intersection and throw it into chat. If not, you can just wait and I'll plot them and we'll check to make sure you're okay. So maybe put a couple minutes up and maybe like 3 or 4. Shouldn't take too terribly long. And then we'll come back and we'll look at what your solution is. So good luck with that. All right. Now it's possible I didn't give you enough time to solve those two equations and plot them. Or nobody's feeling brave with their solution. Either way, I'm just going to kind of whip through it real quick, and then we'll see how many people got the right answer, or if anybody got the right answer. Our two lines are kind of already written side by side, so I don't really need to label them or anything, but I want to get them into slope-intercept form. So what I'm going to do is subtract x from both sides here, and I'm going to end up with y is negative x minus 3. So that's in slope-intercept form. Look at that. Ava, Abby, both got the same answer. That's a good sign. Anybody else on the right track there with those two? Let's check, see how they did. So there's our first line. The second one, I'm going to add 2x to both sides, and I'm going to end up with y is 2x plus 3. Okay, so I'm going to plot this blue line here first. Negative 3 is my y-intercept, 1, 2, 3. And my slope is negative, remember when I have this, it's negative 1 over 1. So I go down 1 over 1. There we go. So I have a few points there. Draw my line. Okay, so there's my blue line. My green line has a y-intercept of plus 3, 1, 2, 3. And my slope is just written as 2, which is the same thing as 2 over 1. So up 2 over 1, there. I can also go down 2 left 1 if I want. And do my best to draw a straight line through those 3 points. All right, so I've drawn my two lines. Now I need to figure out where they intersect, because the whole purpose of this is to figure out where my 2 points cross, or where my 2 lines cross, I should say. So I'm going to identify my solution as somewhere in there. It's really, really close to that exact grid point. It's kind of looking like negative 2, negative 1. And a few of you guys got that. When it says how many solutions are there, is it infinite because you can literally put anything in the equations to equal negative 3 or 3? I think you're maybe a step ahead of me. There's another 2 examples we're going to look at that are going to give us the other 2 possible scenarios. So if you mind holding that thought for just a second, we'll get to it. Where do the graphs intersect? They intersect at negative 2, negative 1. There's one solution, because those lines only cross at 1 point. Now, when you guys get into grade 11, you're going to end up with really crazy situations like this, where you have something like this, a parabola, and then you'll have a line going through it, and it's going to cross at 2 points. So you're going to end up with 2 solutions. But for grade 10, we only deal with linear functions, only deal with lines. So we only are going to encounter where 2 lines intersect. When you move on, you can get some really, really crazy things happening on graphs, and you can have, 1 solution, 2 solutions, maybe 4 or 5 solutions, because once you start graphing some equations, you can end up with 3 or 4 solutions happening. So because the slopes of the lines are different, what are my slopes? I had a slope of negative 1 over 1 and a slope of 2 over 1. These slopes are different. The lines intersect at 1 point. So that might have answered your question, Ava. We're going to get into 2 additional scenarios here where that doesn't happen. So there's only sort of 2 things we can, 2 additional things that can happen. All right. We have 2 additional equations here. Example number 2 again. we're going to look at doing the exact same process. Slope-intercept form to figure out what the equations look like. And then we're going to go ahead and plot those, figure out where the lines cross, and then identify what that point is. So here we go. The first one, I'm going to move everything to the right side here to attempt to get y by itself. I'm going to put the 4x in front of the 8 just because it's going to make my life easier in the long run. Divide everything by 2. 4 over 2 is 2, and 8 divided by 2 is 4. So there's my first line. Let's plot it. Y-intercept plus 4, 1, 2, 3, 4. My slope is 2 over 1, so I rise 2, run 1. And I'm going to go ahead and draw that line. Again, I don't know where the other line is going to intersect it, so I'm just going to draw it all the way across my graph. Second line here, I'm going to add 2x to both sides. Again, I get y is 2x minus 2. All right, y-intercept minus 2. And the slope here is 2 over 1. So I have my another point. 2 points is enough for a line. And that didn't work very well. There we go. Can anybody see perhaps a bit of a problem we're running to at this point? What do we think? What's happening with our lines? Brilliant. They are exactly parallel. Now, isn't it funny that we spent time in the last unit talking about parallel lines, and now, look, it's important that we know what parallel lines are. And as soon as we can identify our lines as being parallel, we know that they're never going to intersect. So there we go. This is the second scenario we're going to run into when we plot these types of equations. So the graphs do not intersect. We can write, they don't. How many solutions are there? Well, there are 0 solutions. Because those lines are parallel, they will never intersect. So the easiest way to identify when this is going to happen is to look at the slope. If the slopes of my lines are the same, then I am going to possibly have 0 solutions. Can anyone maybe jump to the next possible scenario? We've had lines that intersect, so they have 1 solution. We have lines that are parallel, which will have 0 solutions. Is there anyone that can maybe think of the third scenario? And I'm going to give you a hint. It has nothing to do with perpendicular lines, because perpendicular lines will intersect at a 90-degree angle, but there's only 1 solution. Taylor, you're on the right track with 2 solutions, but it's more than that. How could we have straight lines that crossed each other more than once? Like, can you think of how that would maybe work out? What are we going to run into there? I have a feeling some of you are on to me, but possibly not. Let's perhaps look at an example. On the same coordinates, I'm thinking you got it. Let's look at the third example here. I'm going to do the same process again. Slope-intercept form, plot the lines, see what happens. So I'm going to move the 2x to the other side, and I'm going to end up with y is equal to negative 2x minus 1. Okay, so I know my y-intercept's minus 1. My slope is negative 2 over 1. So I'm going to go down 2 over 1. And then I have a line, 2 points. I'm going to connect those points. Now I'm going to do the same thing with the other one. I'm going to subtract 4x from both sides, and I'm going to end up with 2y is equal to 4x negative minus 2. Divide everything by 2. End up with y is negative 2x minus 1. So plot my y-intercept, minus 1, and use my slope, negative 2 over 1. What just happened? I just changed my line from blue to green. What do you notice is going on here in terms of my equations? So we had the idea that maybe there was going to be 2 solutions, but we had straight lines, so straight lines can only cross each other once, ever. Or they can cross each other 0 times if they're completely parallel. But what would you say is happening here when my lines are literally on top of one another? What do we think in terms of solutions for these guys? How do we kind of quantify how many solutions there are? If I asked you how many solutions, they cross everywhere. So no matter where I look on that line, I have a solution. They're literally the same line. They lie on top of one another. So if I looked at this point, I would end up with a solution like right there. I'd have a solution here, I'd have a solution here, I'd have a solution here. Literally everywhere I have solutions. So where do the graphs intersect? Everywhere. And Abby's hit the nail on the head. There are exactly infinite solutions. No matter where you look, those lines are on top of one another. It's a solution. I could check on this kind of little graph I have in front of me. I could go out to, a million and check there. I could go out to a trillion and they'd still be on top of one another. So it's still a solution. So because the slopes are the same and the y-intercepts are the same, we call these coincident lines. It's a fancy math word. And I don't think that it even matters if you know coincident or not. The important thing here is that the lines are on top of one another. You're going to have infinite solutions. Literally everywhere you have a solution. So I mentioned at the beginning of the lesson that there was going to be 3 scenarios we'd run into. We've seen all 3 scenarios now. So let's put them in a little chart. And we will kind of maybe just summarize them. So slopes of the lines, the second we have different slopes, we're going to have exactly one solution. So if we drew a little graph here, I'm going to draw a little graph for each of these. If I have a line here, and then I have another line down here, I have one solution. So I end up with one intersection and one solution. Do I have a solution at 3, -13? I don't think my graph goes to -13. So, yeah, I only go up to 6 there, Alex. So you'd have to actually plug it in and see if it satisfied both equations. If I have lines with the same slope, something there, I would have, we can call it 0 solutions. 0 intersections, 0 solutions. The last one here is coincident lines, where I have lines that are exactly on top of one another. Difficult to draw. And I end up with infinite solutions and infinite intersection points. So those are the three things. If we have two lines, those are the only three scenarios we can end up with. And the whole rest of chapter 7, or unit 7 I should say, we're going to try to figure out if we have parallel lines, if we have lines with different slopes and different y-intercepts or intersect at one point, or if we in fact have the same line or a coincident line that's on top of another line. So that's all we're doing for this whole unit. We're just going to look at different ways to figure that out. It's 10:05. We have about 15 minutes left. I'm going to maybe go through a couple more of these questions. But if you had anything from the previous unit that was like extremely pressing that you wanted to go through before you submitted your learning guide or wrote that test, you could throw that into chat. If nobody has any extremely pressing questions, then I will do a few more examples of this stuff that kind of look like some of the ones that you're going to see in the learning guide. I think I have 3 examples left. You have an extremely pressing question. Fire it in there, Alex. Page 7, number 4 and 6. Okay. Well, Alex, I've already done both of those questions. Graph the line. So we did. How did we do it? We converted it into, we didn't convert it. We found, because it was in slope point form, we already knew the slope was this guy, the m. So 3/5. The point was this 4 and the 5. And remember, when we find the point, you need to flip the signs. So if it says x plus 4, because the general slope point form looks like y minus y1 is equal to m, x minus x1, your equation needs to be in that same form. So if I get y minus something and m x minus something, what is that something going to be? So I guess that was maybe the trickiest part of doing this, is determining what that point was. So in this case, the minus 5 was here, so I put in a plus 5. And over here I had a plus 4, so I needed to put in a minus 4 to end up with the right sign. So my point was -4, +5. I have the slope, and I can go from there. So that's the tricky part of slope point form, is figuring out what that point is, because we have to watch our signs. Think of what the general form looks like. I did this over here as well, and then go from there. Number 6, I think I did almost all of these. Convert the following to general form. Remember, we have to have ax plus by plus c equals 0. A must be a whole number, so it has to be a positive integer. B and c can be whatever you want, as long as they're not fractions. So just to make sure I've done all of these questions for you guys, let's start with this one, and let's get rid of our fraction. So I'll jump way up here. Y is equal to 5/3x plus 3. Want to get rid of my fraction? I'm going to multiply everything by 3 because my 3 is on my denominator. 3 times 5 over 3 is going to give me 5, and 3 times 3 is 9. So 5x plus 9. I'm going to move the y to the other side to end up with 0. So I get 0 is 5x minus 3y plus 9. There you have a splendid. Nobody else threw in any questions, so I'm going to assume that that's it. No problem, man. All right, I want to jump back, kind of hopping all around here today. I'm going to maybe look at a few of these examples, have about 10 minutes, and we're just going to solve them. And the question is a bit kind of misleading, perhaps. It asks determine the number of solutions. So the question isn't asking us what the solution is, it's asking how many solutions there are. So we have 3 choices. We have 1 solution, we have 0 solutions, or we have infinite solutions. That's what your answer is going to be. 1, none, or infinite. That's it. Those are the 3 choices. So we need to look at our lines and compare them. The easiest way to do that is maybe put them into slope-intercept form, because once I've done that, I can figure out if the slopes are the same and the y-intercepts are the same, they're the same line. If the slopes are the same but the y-intercepts are different, then I have 0 solutions because they're parallel. And if the slopes are different, automatically my slopes are different, I'm going to have 1 solution. So let's convert these puppies. I have line number 1, I'll call it. I have line number 2. I'm going to switch them into slope-intercept form. So number 1, x plus y is negative 2. I'm going to subtract x from both sides. Negative x minus 2. My second line, negative 2x, negative 2y is 4. I'm going to move my y to the other side to make it positive on the other side. So I'm going to add 2y to both sides. Then I'm going to move the 4 over after. So I have negative 2x is equal to 2y plus 4. Subtract 4 from both sides. Negative 2x minus 4 is 2y. And then divide everything by 2. Show that step. So I get negative x, or negative 1x, minus 2 is equal to y. All right, so I'm going to compare my equations here. This was line 1. Y is negative x minus 2. Here I have the same thing. So our slopes are the same. If I look at the slope of my first line, it's equal to the slope of my second line. My y-intercepts are the same. Slope of my first line is equal. The y-intercepts are the same. So I can just write something like, these are the same line. The slopes are the same, the y-intercepts are the same. We can call them coincident lines and infinite solutions. So that's all the question was asking. Do we have 1, 0, or infinite solutions? In this case, we have infinite many solutions. Let's look at the next example here. I'm going to convert both of these into slope-intercept form as well. So 4x plus 6y is negative 10. Move the x to the other side. 6y minus 4 equals negative 4x minus 10. Y is equal to negative 4 over 6x minus 10 over 6. I should probably simplify my fractions. Negative 2 over 3x and then 10 over 6 can be simplified to 5 over 3. So that was the first one. My second line, negative 2x minus y is negative 1. Going to add y to both sides. Plus y minus 1, add 1 to both sides. Negative 2x plus 1 is y. So I look at the slopes now. I see this slope is negative 2 over 3, and this slope is negative 2 over 1. So I can just write the slope of my first line does not equal the slope of my second line. So what does that mean? I have two lines with different slopes. It doesn't even matter what the slopes are. As soon as I have two lines with different slopes, I have only one solution. Now, we just kind of look at what's been happening. The first example, our lines were the same. The second example, our lines were different, so we had one solution. The third scenario is that our lines are parallel, and you can probably guess that this last example is going to give us parallel lines, but we're going to do it anyways because we can use the practice. So 3x plus y, negative 1. I get y is negative 3x minus 1. Second one, negative 6x minus 2y is 12. I'm going to move the 2y to the other side. I'm going to subtract 12 from both sides. And I'm going to divide everything by 2. So I can see that my slopes are the same, but my y-intercepts are not. So I could say B1 does not equal B2. What can I gather here? My slopes are the same, meaning my lines are parallel. I can't say that these are the same line because my y-intercepts are different. If the y-intercepts were the same, then I'd have coincident lines. But because my y-intercepts are different, I don't have coincident lines. I have parallel lines and 0 solutions. So that's it. In terms of the learning guide, I had a quick look earlier. The first 3 pages, so solve by graphing, you guys can do that. This same thing, we're going to plot these on the graphs. Linear system, so just getting the definitions on the 3rd page, and then determining the number of solutions like we just did on question 10. So you're good to go up to the end of page 3 on the learning guide. A couple things I'd like to remind you of before we get going here. If you would like to come to archery tomorrow, we're at same place on Enterprise. The address, or sorry, it's technically Cooper, 1771 Cooper, but we find it off Enterprise is a bit easier. Hardcore Archery. Be there tomorrow at about 10:45. We'll have an hour and a bit of archery. If you didn't come last week, you can come this week. It's fine. if you did come last week, you're good to go and you can just shoot as soon as we get there. So we're going to get tons and tons of shots in tomorrow. And I'm sure Mrs. Wood and Ward have warned you, and you guys have likely not forgotten about it, but Monday, you're not going to have math. You guys are at Central doing your English midterm exam. So I understand it's an essay, and that's about all I know about it. But 9 o'clock, Central Gym, and hopefully we'll see you guys both tomorrow at archery, and then on Monday at Central. We have 2 sections left in this unit, lesson 2, lesson 3, and then we'll have a review day on Thursday, and then you guys have the entire break to get the Unit 7 test done. So I'm going to leave it there for today. Thanks very much for those of you who submitted your learning guides from Unit 6. I apologize for not getting them back to you sooner. I will get that done today prior to lunch, and I'm sure we'll see a lot of you guys tomorrow at archery. So have a good weekend if I don't see you. Bye-bye.